Welcome back to part 2. Here we looked at the introduction to system responses, defined the issue of stability for both transfer function models and state-based models, and have looked at the responses of a typical first-order system and second-order system. We wish now to continue to talk about the remaining topics in this unit, that is to focus on higher order system responses, feedback, and performance indices. So let's look at an example of how to tackle or how the location of the poles in the S-plane relates to the behavior of the underdamped system. So in example 1, the question is, in which area of the S-plane should the poles of an underdamped system be located so that the peak overshoot is no more than 10% and the peak time is no earlier than 2 seconds. We know in this case for sure that these poles are going to be a conjugate pair. And in general, we have learned from studying second order systems that the location of the poles themselves is related to the parameter of the damping factor as well as the natural frequency. So in fact, we have seen that this angle is related to the damping factor. And then we can see that this location on the imaginary axis here and this possible location here, axis on the real axis, is also related to both the damping factor as well as the natural frequency. So let's first tackle the peak overshoot. So we have an ambition to keep the peak overshoot to be less than 10%. So if we look at this, we can use figure 5.8. So if you use figure 5.8, we see that the 10% peak overshoot, which is here, corresponds to a damping factor of about 0.6%. Anything that's lower than 0.6% we don't want. So we want the damping factor to be in this range so that the peak overshoot is kept low. We want the damping factor to be at least 0.6. So we've established that the angle here on the complex plane, this angle theta, is determined by the cosine of inverse of the damping factor. So we can calculate this angle, in this case cos inverse of 0.6. We find that the value is around 53.1 degrees. So this gives us 53.1 degrees. And we can check as to what happens when, say, our damping factor is 0.7. When the damping factor is 0.7, you can use a similar calculation to find out that the angle is around 46 degrees or 45.6 degrees, which means we are looking for all of the possible poles which will lie in this area. So we want our poles to lie in this area because the angle has to be less than 53.1. Anything that's less than 53.1 will give us a desirable value, such as 0.7, which is here. So it therefore means, based on the damping factor, we can tell that our suitable area for the location of closed loop poles in this case is going to be roughly here. Now you can calculate this quickly, in fact, in Octave. So in Octave you can, let me just show you. You can make this calculation of the cos inverse by typing in A cos So if this was the Octave command prompt, you can just type in A cos 0.6. The angle that you're going to get is going to be in radians, so you need to multiply it by 180 degrees and divide it by pi in order to get the value in degrees. So you can do that in Octave just to verify. So this this condition of the peak overshoot of less than 10% gives us the first condition in our sketch, which is the angle of 53 degrees. So having used the peak overshoot, we have established that this would be a desirable area of our our poles, whereby this angle is equal to 3 degrees. Now we can use the second issue here, or the second restriction, that the peak time be no later than 2 seconds. What we are saying is that the peak time, which is equal to pi over omega n 1 minus 2, must be it must be no less than 2 seconds. So which means it must have an upper limit of 2. Now what this means is we can show that this means that the pi divided by 2 times 1 minus the damping factor square gives us the lower limit of the natural frequency. And from there, we can substitute to show that the natural frequency has to at least be equal to pi divided by 2. Since you already know the damping factor from the previous calculation, which was 0.6, we know the damping factor, we can just substitute here 0.6, and we can get that the natural frequency is therefore limited to 1.26. We have also established that previously that when you have the real part of the pole, which is here, this real part of the pole, it's equivalent to minus damping factor times the natural frequency. So this real part, this line here, it's bigger than that. It's equivalent to that. So we can calculate that. We can therefore calculate that here that if Wn is at least, if Wn is at least 1.26, if I multiply by the damping factor on both sides, I get that 1.26 times the damping factor will be greater than W. If I substitute, then I will have Wn, try and write more legibly here. Wn has to be greater than 1.26 times 0.6, which is 0.75. So we can see that it means this magnitude, this value, has to be greater than 0.5. So we can draw a line here. This line would be negative 0.75. So since our poles, this value has to be, the poles have to be located whereby this real part is greater than 0.5. It means then that our poles can only be located here and not on this side of the line, not here. but only on this side of the line. So you combine the two conditions, we can say that this ensures that the region of the S-plane where our poles can be located will be marked by, or it's bounded basically by these two lines, this black line as well as this purple line, and the location can only be on the left side of these two boundaries. So let's tackle an example. In this example, we have, for example, to select the parameters alpha and k in T of S, so as to place the poles of the system appropriately to have the settling time of at least 8 seconds for 80% criteria, a peak overshoot of at most 25%. And the question is basically, what should the limits on alpha and k be to give us this behavior? We know that generally speaking, the transfer function of a second order system, it's the natural frequency squared over S squared plus 2 times the damping factor times the natural frequency S plus the natural frequency squared. From these two expressions, if you equate the two, we realize that it means therefore that alpha is equal to 2 times the damping factor times the natural frequency, and k is equal to the damping frequency squared. So these are our two equations here. We'll together call this equation number 1, part 1 and part 2. Now, if we tackle the settling time, we know that the settling time is given approximately by 4 divided by 2. So the settling time is given by equation 5.3, which is basically 4 divided by the damping factor times the natural frequency, and this we say should at most, should be at most be 8 seconds. So we don't want the settling time to be beyond 8 seconds. What this therefore means is that if we look at equation 1, in particular this equation, it means that the settling time here is equal to, it means in fact we can do this. So we can take this equation 1 and then we can say half of alpha is equal to the damping factor times the natural frequency. Therefore, we can say the settling time, which is equal to 4 over the damping factor times the natural frequency, is equal to 4 divided by 0.5 alpha, and this should be greater, this should be less than 8, because then we can substitute this expression, for 0.5 alpha, right? And so this implies that 4 is less than half times 8 times alpha, which implies that alpha has to be greater than, let me make it simpler here. Let me just say, which implies that 4 is less than 4 alpha, which implies that alpha has to be at least equal to 1. So this is the first condition that we get for the parameter alpha. So we have just established from the previous slides that the first condition that we get on the parameters is condition on alpha, which means alpha has to be greater than 1 so that the settling time criteria of at most 8 seconds can be satisfied. Now we have also established that we have this following relationship for what we call in this case equation 1, and this following relationship for what we call in this case equation 2. And so what we can do, in fact, is to show that we can show that from here that it means k, the root square of k, is equal to the natural frequency. So having done that, let's now focus our attention on the issue of the peak overshoot. So we are told that the peak overshoot must be at most, which means the peak overshoot must be at most 25%, which means the peak overshoot can never go beyond 25%. If we look at this figure, which discusses the peak overshoot, we can see that a 25% peak overshoot is around here, and this corresponds to a damping factor of around 0.4, which means the peak overshoot of 25% corresponds to the damping factor of 0.4. And if we want to limit our peak overshoot to this value, it means that the damping factor has to always at least be any value which is higher than 0.4. So we can tell then that this implies that the damping factor has to be higher than or equal to 0.4. So 0.4 is the lower limit. Now, having established that, if we take from 1 we can show that the damping factor times 2 times the natural frequency is equal to alpha. It implies that the damping factor is equal to alpha divided by 2 times the natural frequency. And then we can substitute 2 here. So we can get an expression in terms of k. If we substitute for 2, we cancel that and draw a line here. We can get an expression for k. We can get an expression to show that the damping factor here is equal to alpha, which is equal to 2 the square root of k. And this, we are told, has to be at least 0.4, which now means that we can write that alpha has to be greater than 0.8 square root of k, right? Or alternatively, we can show that 0.64, if you take the squares, k has to be greater than alpha squared, which would therefore mean, as our condition on k, it's that k has to be greater than alpha squared divided by 0.64. And this is an example of another condition. So we have this first condition, condition number 1. We also have the second condition, condition number 2, for the parameter values of alpha and k. So alpha has to always be 1, at least 1, and when that is the case, we also know that k has to be at least bigger than alpha squared divided by 0.64. We can give an example, for example, we can give an example of such parameters. We can set, say for instance, alpha has to be equal to 10, and if we set alpha is equal to 10, we can quickly see that if we substitute into 2, this would be 100 divided by 0.64, which is something around 156. 156, which means k has to be greater than 156. So we can pick k, say for example, which is equal to 160. So this would be an example of the parameters. These parameters would work to satisfy this criteria. We now turn our attention to generic higher order systems, having got the basics of how the first order systems work, and then second order systems. We have learned, or we have reminded ourselves of these lower order systems because it turns out that higher order systems can be approximated using equivalent lower order systems for the purpose of analysis. Now, this comes from the fact that we can observe that the response of a control system is dominated by just a few poles that lie very close to the imaginary axis, and these poles are called dominant poles. So if a system has multiple poles, many of which are of the imaginary axis, those that lie close to the imaginary axis will dominate the response. Any far away in the negative poles, that is poles in this direction, can be ignored because their impact on the response will almost be very minuscule. As much as these other poles can be ignored, it is important to note that some of the zeros which are close by to the dominant poles have a big impact on the response of a closed loop. So one needs to be mindful of these closed zeros. So what we are saying here is that if, say for example, you have a transfer function like this with 3 poles, and you notice that this particular pole here is located at negative 101, this particular pole is located at negative 52, and then you have a pole which is located at negative 1. Because of these poles, the one at negative 52 and 101, these ones are very, very far away from the imaginary axis when you plot them on the S-plane. So if you're going to plot this on the S-plane, the one which is negative 1 might be here, and then the one that's 50 would be somewhere here. So you'd have a pole here and you have another there. This pole is going to have a minimal impact on the response of the system. That means that we can understand the response of this system by simply looking at the response of its approximate transfer function. So this transfer function can therefore be approximated to this particular one for purpose of analysis. So in that case, we analyze this third order system as though it behaved similar to the first order systems, and we can use all our analysis tools that we have learned from how first order systems behave in that way quite easily. Another example here is a system which has a conjugate pole pair as well as a distant pole in the negative 78. For the same reasons, this third order system can be approximated to this second order system because these poles will be much closer than these poles to the imaginary axis. Generally speaking, therefore, we can say if you have a transfer function of a conjugate pole pair and a very far away pole in the negative as well as a closed by zero, this transfer function can be plotted on the S-plane this way. You can plot here the conjugate pole pair and this with this as the minus zeta omega n as the real part of the pole. And we can also plot here, for example, at minus a we plot this 0, and then somewhere further down the line in the negative we plot this further away pole. So what we are saying here is that these three items are the ones which are going to dominate the response of the system. In fact, these two are going to be called the dominant poles which dominate the response, but the response will also be affected by this pole. For that reason, we can approximate this very function into this one, which is much simpler and to analyze. As a rule of thumb, we say we can do such an approximation when the close by pole is at least or around more than 10 times. In fact, we can do this when the furthest pole is at least or around more than 10 times as far away from the imaginary axis as the closest pole. So the furthest is like 10 times away from that which is close. So we can tend to ignore the impact of these far away poles. For example, here you see this pole is at 1. This one is at 52, which is much more than 10 times. This one is at 101 of this dominant pole. So to recap, we have just established that with regard to the effect of the pole, the response is dominated by the dominant poles which are close to the imaginary axis, and the effect of the pole, any other pole such as this one, decreases with increasing distance from the imaginary axis. So as the pole goes that way, its impact goes down. Its impact goes down as it goes that way. Take for example here, let's say you have a system which is a second order system, and this second order system has a pole, for example, located, a distant pole or a third pole located at this point, and then we want to see how that pole affects the overall performance of the transfer function. So let's say now the adjacent poles have this damping factor. It therefore means that we can use equation 5.16 to substitute and find the peak overshoot if this system was purely a second order system. So if it was purely a second order system, we see that our peak overshoot will be around 20.53 according to the calculator. So this is for a purely second order system. Now, if you have a system with 3 poles, in this case, this one's plus this one's plus these 2, you can see that the further away you increase, you remove this third pole, the closer in terms of just the peak overshoot, the closer to the type of response that you'll get, which is very similar to a purely second order system. So This third order system, at this stage where the third pole is very far away, is at -20, it is going to behave very similarly to a purely second order system. We have also been made aware that a zero which is close to this dominant pole has a bit more complex relationship, or has a bit more complex influence on the behavior of on the behavior of the overall transfer function or system. So let's say you have a zero now at z is equal to minus a. So your zero is it's -a. Now we will see that the response with which the system will give you will be closely related to this ratio, a divided by damping factor times the natural frequency. So depending on that value, you will see that you would get different behavior. If you look at this graph, for example, here, so this graph shows the real part of the pole divided by the real part. So the real part of the zero divided by a real part of the conjugate poles. And we show that ratio as a function of percentage overshoot. We can clearly see that, for example, these are for the different values or damping value factors. We can see, in fact, that for the same damping value, say for example, so this is the same damping value, we can observe that as this ratio increases, that is, as your A becomes larger, which means as your zero goes further and further into the left hand side, you will see that then your peak overshoot changes from one big value to a small value, right? This is what it shows. So as your pole goes further and further and further away, the peak overshoot will change, become less and less. However, the way it changes is not very straightforward. So which is why you have a graph such as this one to illustrate them. Another illustration here is that this value A, B, C, D, these are the values of A divided by the damping factor times the natural frequency. You will see that when this is equal to 5, which is the A, when this is much large, you see that the peak overshoot becomes small. But as this value goes higher, then what happens is that the peak overshoot increases. And so this graph, in fact, is consistent with what's happening here. But the key message here is the zero that's close to the dominant poles also has an impact on the transient response of the overall transfer function. So for a higher order system, let's consider the following example. Analyze the behavior of a third order system. After analyzing, what are the approximate values of the peak overshoot, settling time, and peak time? Remember, we in actual fact do not have generic formula to describe the behavior of third order or higher order systems. But what we rely on is the fact that higher order systems behave like lower order systems as long as they are dominant poles and zeros. Now, in our analysis, we see that the transfer function of the system is of a third order of this form, but it would be more convenient to work with that transfer function in this order. Because in this order, we can see two things. We can see that there's a conjugate pair of poles here, and we also have another pole on the real axis. For the zeros, we see that there's only one zero. So there's 3 poles, two of which is a conjugate pair, one which is on the real axis, the other is the zero. In fact, we can plot this on the imaginary axis, the real axis, GW axis. We can plot this. We can plot a zero here at -2, and a bit further down the line here, we can plot a pole. So this pole. We know that the structure of for a second order system, the structure of that second order equation is going to be of this form: twice using this structure, we can see that in fact we have 2 times the damping factor times the natural frequency is equal to 1, which means damping factor times the natural frequency is equal to 0.5. And this value always gives us the distance of those, the distance from the imaginary axis on the distance from the imaginary axis of the conjugate pole pair. So we know that the conjugate pole pair will be located along this line, whereby we have minus half here. So the conjugate pole pair is going to be somewhere here. For this reason, we can see that in fact what's happening here is that the pole here is very far away from these poles. So 6 is much bigger than 0.5. In fact, it's more than 10 times bigger. It's more than 10 times bigger. So which means for this third order system, the behavior of this third order system is going to be dominated by only these 3. These poles and that 0. That's what we know. So we can ignore the impact of this pole. So this one can be ignored. We can ignore the impact of this pole. This can be ignored. So we know that then we can approximate this transfer function just using those 2. One of the first things that we need to approximate, that we need to consider when you approximate this function, which I've neglected to mention previously, is we need the steady state value gain. So we need the steady state gain of that transfer function. That is, what is the value of t at s is equal to 0. So we want the steady state gain first of all. We want to make sure that when we approximate this transfer function, the steady state gain remains the same. So in that case here, we will have the limit of t of s going to 0. This is the same as saying having 6 times 0 plus 2 divided by 0 plus 0 plus 4 times 0 plus 6. So if you look at this, now this is equal to having 6 times 2 divided by 4 times 6, and so if that cancels that, we see that the answer to this is simply 0.5. So the state gain of this is simply 0.5. So we need to make sure that when we approximate it, we keep it at 0.5. So our approximate transfer function then is, we keep s plus 4, and then on top we keep s plus 2, right? And on top we keep s plus 2. We look at here, what would be the steady state gain here? The steady state gain here is going to be when S is equal to 0, you're going to have 2 over 4. 2 over 4 is equal to half. So which means here the number that will remain here is simply 1. To make sure that the steady state gain of this approximate transfer function is the same. So it means therefore we can approximate this transfer function using this value. By comparing our approximate transfer function to the generic one, we can see that we will have two equations. The first one is an equation which tells us about the real part, the size of the real part, and the second one tells us about the square of the natural frequency. Now, we can use that from 2 to, we see that the natural frequency is equal to 2, the square root of that n. So which means we can use equation 1 to calculate the damping factor. So damping factor in this case is going to be 0.5 divided by W, which is equal to 0.5 divided by 2, which is basically 0.45. So at this point, you would think then we would simply come and estimate the peak overshoot using this graph. So we would go here and then estimate that the peak overshoot should be around 25%. This would be wrong, however. So this is wrong. The reason why this is wrong is because it doesn't take into account the impact of the 0 that we have here. Because our system would have a 0, and the 0 which is close to this, which is a bit close to our dominant poles. So in that 0, we know that it means we have A being equal to 2. So we need to use this graph, which shows how the behavior is going to be modified. So if we take A over omega times the damping factor, we see that we'll have 2 divided by, from equation 1, if we take that from equation 1, we will see that this is 2 divided by 0.5, and this is simply going to be equal to 4. Now we have 2 points here in our axis. We have a damping factor of 0.545, and we have a sorry, this should be 0.25. My maths was not right there. 0.25. This should be 0.25, and this would have resulted in something like damping factor of around 40 something. If it was a purely, if it did not have zeros, then we were expecting a damping factor of around 45%. But like I said, this we can't use in this instance. We have to use this graph. So we have these two, a damping factor of 0.25, and as well as this ratio of 4. So in that case, we need to look at our graph here. We look at this axis to see if we have 4 on this side, and on the damping factor side we look at damping factor of 0.25. so 0.25 will be somewhere around here. So we look at what these two lines meet. So these two lines will meet around here. Right. So we see that our damping, whereas if it was a purely second order system with no poles, we're going to expect the damping factor, an overshoot of around 45%. In this case, our peak overshoot is going to be much bigger than 45%. So it's going to be something that lies between 50 and 100, definitely above 50. And it looks like it looks like from our graph, our answer for the peak overshoot should be around 50, 60, 70%. So we should be expecting a peak overshoot of around 70%, as opposed to a typical peak overshoot of 45%. So this becomes our first expectation. So in the example, we can simulate in Octave the behavior of this system. First of all, we can take this blue transfer function, the actual transfer function, and simulate it. And the result for that is we're going to get this blue line. And then we can take also the red line here. This approximate transfer function is simulated. So what you can see in Octave is that the two responses are very close to each other. Indeed, the approximation has a very close relationship with the actual transfer function, even though it's not exact. And the overshoot, because this is the expected steady state error. Remember, our steady state error was around 0.5. The steady state value of the output was around 0.5. You will see that this peak overshoot here, which is way above 50%, it can be seen here. So this would be the code from lines 1 to 13. This would be the code that you would type into the Octave command input in order for you to achieve this simulation and compare for yourself. Turning our attention to the penultimate section of this chapter or unit, we will relook at feedback systems, and we have initially indicated that feedback loops have a number of advantages in control systems, especially when you're looking at the introduction in Unit 1. We can see in this example, this is a good example of a feedback system, whereby you have your input, which is R of S, and you have your output, which is Y of S. The other inputs which occur in the system is this one which you can control, which is D of S. This is called the disturbance. And in the feedback loop, whilst doing a measurement, you also have another input, which is the noise, measurement noise, which you cannot control. So typically we will have a negative feedback system. The disturbance will take it to be a positive input, as well as the noise to be a positive input. So the feedback system itself is built to have the input to be able to control the output based on the input. But as a consequence of the natural order of things, you tend to have disturbances. You will also tend to have measurement noise because of that. So in this case here, you have a plant control function of transfer function of your controller, and then you have your transfer function of your plant. So there are three basic uses for feedback. The first primary one, which is key, is stabilization. When an open loop system is unstable, you may tend to put it in a feedback loop so that we make it stable. Another aspect of that is to enhance performance, and feedback can be used to enhance both the transient and steady state response. In the transient performance, it can enhance the speed of response. Your rise time can be made to be very quick by tweaking your controller. You can also enhance your steady state response. For example, you can reduce your steady state error. And the other primary important issue in terms of feedback is that it can be used to reject the effect of feedback. So it's the effect of disturbances. So it can be used for rejection of disturbances, and it can also be used for suppression of the noise. So you can suppress the impact of the noise signal that you are receiving on your sensor. You can also reject the effect of your disturbance. Just as a recap, we'll look at now the let's look at now the transfer function of a typical closed loop control system. So in this case, you will see that when you calculate the transfer function, I'll just use the letters here. Your y, your output y, if you look at the output y here, it's simply equal to the transfer function g, this g multiplied by the input that comes here, and the input that comes there is the disturbance plus u. So the input that comes here is the disturbance, the u plus the disturbance. So y is equal to d times u. However, you see that the input u itself is equal to the controller transfer function multiplied by the error signal. However, you can break down the error signal here, because the error signal you see is the input R minus whatever is coming out from here, and whatever is coming out here, it's going to be h times y here, minus h times y. So substituting that, this becomes my equation 2. So if you take 2 into 1, we have y being equal to g times d times d plus u, but u is equal to gc times r plus h y big bracket. So this is negative. So then we have y being equal to g d plus gc times r minus gch times y, which implies that we have y times 1 plus gch being equal to, if you take this term to the other side, gd plus gc times r. If we divide by this term, you will see this implies that we have y of s being equal to g times g of s times d of s, all of this divided by 1 gch plus gc divided by 1 plus gch of s times r of s. Now what you see in this is that this term, normally we call it the forward loop transfer function. We call that the forward loop transfer function, and this term here becomes the transfer function of the disturbance. So it shows you the contribution of the disturbance towards the output, and then this we simply call it the closed loop transfer function without the disturbance. So we simply refer to this one as the closed loop transfer function without the disturbance. So we see that the closed loop transfer function it's equal to the forward loop transfer function divided by 1 plus the forward loop transfer function times the lead times the feedback transfer function. And we see that the disturbance transfer function is equal to g divided by 1 plus the feedback transfer function. the forward loop GC times the feedback transfer function. Let's look at the tracking error, how it affects the performance of the feedback system. How a feedback system enhances performance of a control system. In particular, we look at the tracking error. We look at, in this case, the feedback loop, which has disturbance and a feedback sensor h of s. We have established that the transfer function of the closed loop is given by this equation, where you have r of s is equal to y of s is equal to gc plus gs of s on top and below 1 plus gc times g times h. And using that, we know that the tracking error is the difference between the input r and the output y. And when we substitute for y into that equation, we see that it gives us the expression of the tracking error as this similarly complex expression. If we simplify things for unity feedback when h of s is 0, when h of s is 1, we see that the tracking error is simply 1 over 1 plus g, the forward loop path, times the input. So this is 1 over 1 plus the forward loop path gain times the input. And so we can see, in fact, before we go to the state error, we can see from this equation that what happens is that the bigger the forward loop gain, the smaller the tracking error. So which means feedback can reduce the tracking error by just simply increasing the forward loop path. When we talk about steady state error, we are talking about the function e of t as t goes to infinity. We have established that using the final value theorem, in fact, we can be able to calculate this in the s domain, because the function e of t going to infinity, when st goes to infinity, is the same as having s times the error function in the s domain times s as s goes to 0. So we can do that calculation simply as well. So sometimes you will see that the system that's been controlled is affected by some modeling errors. So modeling errors can be a big source of disturbances. For instance, you could have some inaccuracy when estimating some parameter. For example, when you are doing a system identification due to noisy data that you have been using. A robust system, or a system, is said to be robust when it has little sensitivity towards the modeling error. So feedback helps with doing that. And we also hope to keep the tracking error, or to maintain the tracking error as low as possible, in spite of any modeling errors that may have occurred while we were modeling our system. A quantitative way of assessing these modeling errors is using what's called sensitivity. And sensitivity is defined as the ratio of the changes in the transfer function to the changes of the process transfer function g. So it's the ratio of the changes in t to the changes of the process transfer function g for a small incremental change. So what we are saying is, how does the transfer function t change if there is a small change in the process transfer function g. So this can be summarized by this equation, and we see that st of g, that's how sensitivity is written, the sensitivity of t with respect to g will be equal to the partial derivative of t with respect to g times the partial derivative of t divided by t over the partial derivative of g divided by g. Excuse me. Now we can calculate the forward path closed loop sensitivity for a unity feedback system as shown here. So if we have a unity feedback system like this one, we call it a unity feedback system because here in the feedback loop you just have 1. You don't have a gain here. The gain is 1 in the feedback in the feedback loop. That is, h of s is just simply equal to 1. So we'll see that according to this definition, when you use this definition of calculation, you see that our t of s is equal to gc times g of s divided by 1 plus gc times g of s. So you have already established this as our transfer function. Now, if we do a partial derivative of t with respect to g and multiply by g over t, this should give us the first differentiation. This will give us this result, and if you manipulate these variables, you will see that ultimately we'll get equation 4.3. And with equation 4.3, we can in fact avoid doing this calculation of derivatives and simply use equation 4.3 to substitute the values into equation 4.3 in order to find the sensitivity easily. In many other practical cases, our interest would be to find the sensitivity of the overall closed loop transfer function with respect to the changes in the parameter that we may feel that it may be inaccurate. So if we are looking for such a sensitivity, we can use one way of calculating this is to use the chain rule. So the chain rule simply says the sensitivity of the closed loop transfer function with respect to a parameter alpha is equal to the sensitivity of the forward path transfer function that we have just shown previously, multiplied by the sensitivity of the forward path transfer function with respect to alpha. I'll repeat that again. I'm saying the sensitivity of t with respect to alpha is simply equal to the product of the sensitivity of t with respect to g times the sensitivity of g with respect to alpha. So remember, we have established this relationship as equation 4.13, that the sensitivity of t with respect to g is can simply be calculated without doing any derivatives by simply substituting g of c and g. And what this means that is our job is cut in half now. All we need to do is to calculate the sensitivity of g with respect to alpha and then multiply that with STG. So let's look at an example here. We are to calculate both the open loop and the unit feedback closed loop sensitivity to a parameter to the transfer function with respect to a parameter alpha. So we see that transfer function here is simply equal to 2 over s squared plus 10 times the alpha that we are looking for. Now the definition of sensitivity says that g with respect to alpha will simply be partial derivative of g over partial derivative of alpha times the g at the bottom and the alpha on top. This is by just simply looking at this. So by definition, this would be the sensitivity. And so, just divide here. We can see that when we look at this, we see that this is the same as the partial derivative of 2 over s squared over 10 times alpha over partial derivative of alpha times alpha itself times 1 over g, right? And so if we compute this part, we see that we are left with 2 times s squared plus 10 times alpha times 1 over g. 1 over g is simply the inversion of that, which is s squared 10 over 2 alpha. Now you'll quickly see that this will cancel that, that will cancel that, that will cancel that, and you'll soon be left with simply as 1. So which means the sensitivity of G with respect to alpha is going to be 1. So for every small change that happens in alpha on the transfer function, that change is just simply amplified by 1. It will affect the output by 1. So that's what basically it means. This is more like a slope. So if this value was 2, it would mean that for every small change in alpha, there will be twice as much impact on the resulting output. So now we cross over to the closed loop transfer function. We can easily show that the closed loop transfer function is equal to this by simply looking at that the transfer function of the closed loop is going to be 1 over 1 plus G. So it's going to be like this from our previous experience. So this is going to be our closed loop transfer function. So we can substitute that and then we'll get this value. However, we do not need, because in actual fact, if we were to calculate the sensitivity of the transfer function with respect to alpha, we are going to calculate the partial derivative of the transfer function times the partial with respect to alpha times t over alpha itself by definition of the sensitivity function. Now we can see that it will not be a pretty sight here to try and complete this, because this is a fraction. Alpha is at the bottom, is also on top. This derivative might take us quite a while to complete. Instead of doing this, we will use the chain rule here to show that the sensitivity with respect to alpha is simply equal to the sensitivity of t. This sensitivity times the sensitivity of alpha with respect to g. This we have already calculated because it's done here. It's equal to 1. We already know. What we need is this sensitivity of t with respect to alpha. However, we have this equation here. So we can see that for our particular case, GC of S is equal to 1. That is, the controller transfer function is simply equal to 1. So it means, therefore, that we can write the sensitivity of G with respect to T using equation 4.13. This equation of 4.13, we can write this as 1 over 1 plus G of S. And this will give us 1 over 1 plus G of S, we substitute alpha over S squared plus 10. And then this is going to be equal to, we multiply by S plus 10 on both sides, on both the top and the bottom. This is going to give us S squared plus 10 at the top divided by S squared plus 10 plus 2 alpha. So this is the sensitivity of the closed loop transfer function with respect to G. Now we can go back to this equation, which I will call equation 1. You will use 1 then to say the sensitivity of alpha of t with respect to alpha is simply equal to st of g times 1, and st of g we already know, it's s squared plus 10 over s squared plus 10 plus 2 alpha. So our answer, if you write it clearly in this box, sensitivity of alpha with respect to the closed loop, it's simply s squared plus 10 over s squared plus 10 plus 2 alpha. So we see in this case that the sensitivity here, if we look at the case where for the state case where t goes to infinity, that is alpha, that s goes to 0, we see that the sensitivity of the open loop will simply be equal to 1. However, the sensitivity with respect to the closed loop at that stage where s is equal to 0 is going to be 10 over 10 plus 2 alpha. So this is likely going to be less than 1. This is likely going to be less than 1 depending on the value of alpha. So if alpha is 0, it's going to be 1. If alpha is even more, it's going to be much less than 1, which means the closed loop will be less sensitive to the changes in parameter alpha as compared to the open loop. So modern control systems, at the heart of it, it's about trying to optimize the performance of systems. That is to find the best. And the way the best is defined normally could be qualitative. But what we need to do is to have a definitive explanation of which is the best, or indication of which is the best between any 2 or 3 systems. So the best system to be used can be measured quantitatively, in fact. And what we use there is it's a positive definite integral, and this positive definite integral value is called a performance index. So generally, a performance index is a measure of the performance of a system. Normally, it's commonly a function of the error and an integral for that matter as well. Control system that minimizes the performance index is called optimal. So there is a variety of these performance indexes or performance indices, and we shall discuss only 3. Your literature text will give you 4 of them. The most common one is called the integral square error, which is the EICSY, and you can see that it's an integral of the error squared with respect to time, and the integration is up to some time t. You may also have the integral of the absolute error, magnitude of the absolute error, IAE, or the time integral of the integral of time multiplied by the absolute error, ITEE. And it's important to note that there may be some practical meaning to some of these indices. For instance, when designing control systems, for example, you may want to minimize energy usage or fuel consumption in an aeroplane, energy usage in an energy consuming plant, or you may want to minimize, for instance, passenger discomfort in a car. The selection of the limit t, it can be a bit arbitrary, and but what tends to happen is that t is chosen to be sufficiently large so that the performance is measured all the way up to when the system settles up to the settling time. And then it's also crucial to note that a system may be optimal as far as one index, but not necessarily the other. So it may be optimal as far as ISE, but not necessarily to IEA. For example, if we consider the figure at the bottom left, we see that, for instance, this figure shows an example of a second order system which has a damping factor that has been varied, and we are looking at the index or the value of the damping factor, that optimizes the index. For example, on the ITAE, we see that the index is minimum at this point. So the value of the damping factor that minimizes the index might be 0.7 in this case, if you look at the graph. However, if you look at another index, ISE, you see that the index is minimum at around here. So the value of the temperature factor that minimizes it might be 0.6 instead, which is different from 0.7. So a system may be optimal with respect to one index, but not necessarily optimal with respect to another. Looking at in detail now at the ISE, we can see, for example, how the ISE is calculated for using the following series of figures. Now this is the step input, and this is the output response that's obtained, which is y. Now the error here, which is simply equal to r minus y, its function will look like this. And if you take the square of the error, you would see that then you have a positive function, which looks like that. And when you sum everything, this will give you the ISC function, or the value of the function ISC, to look like that. Now, what we will observe here is that the ISE tries to minimize the square of the error. You see that, for example, in portion number 1, the square of the error is big, and in this portion, the square of the error reduces. So what the system will try and do in this case is to try as much as possible to ensure that this gap is small, right? So generally speaking, for the ISE will avoid excessive underdamping, because underdamping causes overshoots to make this thing smaller, and it will also try and minimize excessive overdamping, because overdamping will result into a delayed response here to get to that value. So in that case, this will make it also small. The other important thing is that the use of a square in itself, it's more convenient for calculations and analysis. So this is why it's used. The ITAE, which is defined as the integral of the absolute error times time, it will, on the other hand, try to minimize two things, or to reduce the effect of two things. The first category is large initial errors, because initially t is small, but when t is small, if this is large, then it will look at the error, the large initial errors, and later it will also try and reduce the impact of errors which occur late, because when an error occurs late, t will be much bigger later, much bigger amount, so it will punish any error that's big that occurs late. So another way of looking at this, looking or contrasting between the two performance indices is to look at ISC versus IEA for the same or a similar transfer function. You see that, for example, when we look at the transfer function that has n is equal to 2, this particular one, you will see that the IAE and the ISE, the ISE responses that are optimal are very different. For the ISE, you see this is quite highly underdamped when compared to the one that optimizes the IEA. So I think this also goes on to further emphasize that even between ISE and IEA, the system which is optimal with respect to one performance index may not necessarily be optimal with respect to another performance index. So if you look for instance, the ITAE, they are known optimal uh, responses, or the structure of the optimal closed loop response transfer function for the ITAE can be summarized as the following, with the following coefficients. So this, for example, when you see second order system, that's optimal for the step response. This is that particular second order system, and that second order system will have the following parameters, which is 1.4 here in the middle. Even in the case of a ramp response for a closed loop transfer function of this form, you can see that a table can be constructed of all of the optimal coefficients for that particular structure of a function. So if you compare these two, you will see that these are not necessarily the same. But the good thing is you can be able to tune your closed loop transfer function so that it meets or is the same or it conforms to this. So some of these structures. At this point, we have considered all of the learning objectives. This in part 1, this in the laboratory exercises, and all of these 3 now in this part. And I therefore urge you to go and look at the tutorial to attempt to answer those questions and complete the tutorial assignment in order for you to understand the concepts even better. Please do go ahead and refer to the relevant sections of the book as your reference. Use the study guide should you have any issues with identifying which sections are relevant for which topics.